Hello, calculus students. This is Mr. Schaefer. I have for you a mock exam that I'm calling AB3 and AB4. Just another round of a practice exam for you in preparation for the 2020 AP Calculus exam. So this is a non-calculator tabular FRQ, and we see that there's a table of values at the very beginning. Remember that in calculus, we really focus on these approaches: tabular, numerical, graphical, and verbal or analytical. So there's a lot of different ways we can do calculus. And this is just one way, and we're going to see how we can really tackle a number of different concepts within this FRQ. So thanks to Patrick Cox, who wrote this FRQ. It's an excellent, really outstanding resource for students who are looking to prepare for their AP exam this year. So to dive in, the intro is here. I'm going to actually just go to part A, and we'll just start working through this walkthrough of the solutions together. So here, g is defined, by the way, as this integral function, and then h down here is a piecewise function. But notice that within h, we have a little section here that is defined as an f input argument. So notice that piecewise function for h when we come across the problems moving forward. Letter A says to find the second derivative of g in terms of f and f prime. So my definition of g is up here. Let's find g prime. I'm going to use the second fundamental theorem of calculus. We're going to take that upper bound and plug it in to wherever we see a input variable within the integral itself, in the integrand. So rather than f of t, it's going to become f of 3x squared. But remember that we also have to multiply by the derivative of that upper bound. That's a chain rule step. The derivative of my upper bound is going to be 6x. So I need to multiply that by 6 times x to get the first derivative of g. So the second derivative of g will then become the derivative of my first derivative. And notice now I'm going to need to use product rule. So here's my first component, and then there is the second component. So what I teach my students is derivative of the first. So f prime of 3x squared. Chain rule once again. Derivative of the first times the second. So here's the derivative of the first times the second plus the first times the derivative of the second, which will just be 6. And that's pretty much good enough for me. No need to simplify and join any like terms or multiply variables together. I'm okay right there because that is the definition of g double prime. And at this point, with 25 minutes on the clock, I'm okay stopping right there. Okay, so g double prime, C above. Letter B says, explain why there is a value of c on the interval 0 to 12 such that the derivative f prime of c is equal to -1. I'm being asked to verify the existence of a derivative value. And I'm thinking right away that there's going to be a mean value theorem connection here. In order to prove the existence of a derivative value, consider using the mean value theorem. Now, we can't use MVT before we first establish continuity and differentiability. By the way, this was part A. I'll call that part A. Here's my work for part B. So let's see, is function f continuous and differentiable? Well, it says in the beginning here that f is differentiable. And if it's differentiable, the function must also be continuous. Let's write that down first. F is a differentiable. And therefore, continuous function. Differentiability implies continuity. So now I can actually use MVT. We have to show the difference quotient. The interval that I was given here was 0 to 12. So let's find f of 12 minus f of 0. Divide that by 12 minus 0. So what I'm doing here is finding the slope of the secant line, and I'm wondering if that slope of the secant line is going to match the derivative element in question, which in this case is -1. If they match, then there is some c value on the interval where the slope of the secant and the slope of the tangent will be parallel. Or basically there is some c value where that will be a true statement. So f of 12 is given as -2, and f of 0 from the table is 10. negative 2 minus 10 divided by 12 minus 0 is equal to negative 1. Therefore, by the mean value theorem, make sure you state MBT, state the name of the theorem, there exists a number x equals c on the interval 0 to 12 such that the derivative value at c is equal to negative 1. So there's your mean value theorem proof. Moving forward to letter C. Find the value of x where g has a relative minimum and so I really don't need to use the extreme value theorem or the candidates test. I'm just going to use the first derivative test for extrema here. But first, let's find the critical points on g. So where does g prime equal 0? When in doubt, write a derivative and set it equal to 0. G prime of x is this expression from part A. And I want to know where that expression is equal to 0, because that's going to help me find critical points. So either this f function is going to be 0, or this little 6x is going to be 0. So I have one critical point of 0. Over here, what function input will give me a 0? If I check the table, the input of 9 right there will yield a 0 on function f. So that means that this 3x squared has to be 9. And x squared, therefore, is 3. So my solutions for the critical points would be plus or minus root 3. At this point now, I've established 3 critical points of negative root 3 and 0 and positive root 3. If we create a sign chart where we analyze the first derivative of g, I'm looking for where the derivative actually changes from negative to positive, and I'll save you a little bit of time here. My intervals will go from negative 5 to negative root 3, negative root 3 up to 0. This sometimes just helps me make test points. And I don't know that you would have all this time to really establish intervals on a FRQ, but this is what you'd want to do. You'd want to find the locations where we have a sign change on the derivative of g from negative to positive. And it looks like only 0 is where that happens. So I will say that g has a relative minimum at x equals 0 because g prime changes from negative to positive. There's my justification, first derivative test. Okay, letter D. Letter D is, it says here, g of x equals this integral, evaluate. I'm going to use u substitution on that problem because I can kind of see an inside function here of cosine. Its derivative is negative sine x, so I can do some clever substitution to make that work. So let's see if I can pull this all together. Let's see here. Running out of space, I'll just write it down here below. D. Let u equal cosine. So du is negative sine, or negative du is sine of dx. So to complete the substitution, the integral will then become the integral of negative 1 du f prime of u. And then don't forget to convert the bounds. So my new bounds, using cosine up here, u of 0 would be 1, u of pi over 2. My new upper bound is going to be 0. So there's the substitution. I'm going to actually flip the bounds. And if I flip the bounds and call that 0 to 1 of f prime, that's going to negate the sign of the integral, so that negative will just go positive. And now I have a pretty straightforward FTC antiderivative here. F of u from 0 to 1 is just f of 1 minus f of 0. And from the table, I can find out that those values will equal negative 5. Moving on to letter E. Given that f prime of 3 is equal to -2, show that h is differentiable at x equals 4. So for best practice here, we should really show that h is continuous at x equals 4. So I'm going to let you work that out, prove continuity, but then once, I'll save the trouble to tell you that h is continuous at x equals 4. We should show that proof. I'm going to go down to the part of the proof where we're actually going to prove differentiability. So first show continuity at x equals 4 using our 3 criteria. But then to prove that the function h is also differentiable at 4, we need to analyze both the left and the right-sided limits as x approaches 4 of the derivative h prime. So here's what I'd write down. The limit as x approaches 4 from the left of h prime. Let's find out what that equals. In this case, that'll be the limit as x approaches 4 from the left of f prime of 1/2 x squared minus 5. Chain rule times the derivative of the inside, which is that. Let's try direct substitution. So what is f prime of 1/2 of 4 squared, or 8 minus 5, so f prime of 3, and then times x, which is 4. F prime of 3 in the problem was given as -2. So -2 times 4 gives me a limit of -8. Let's check the limit as x approaches 4 from the right of h prime. So that would be the limit as x approaches 4 from the right of simply -8 is the derivative, and that equals -8. So in conclusion, I might say this: therefore, the limit as x approaches 4 from the left of h prime equals the limit as x approaches 4 from the right of h prime, and therefore the limit as x approaches 4 overall of the derivative exists, and that equals -8. So therefore we can say that h is differentiable at x equals 4. Make sure we use limit notation, both left and right side limit notation, in this sort of equation sentence format to prove continuity, and also here in this case to prove differentiability. One last part here. Letter F. Letter F says, let k be defined as the antiderivative of f. Right away, that means, I'll do part F over here. If k is an antiderivative, then if I integrate function f, I will end up with k plus c. And if I differentiate both sides, then that'll become simply f equal to k prime. And it's really that statement that we're going to be looking at here in a little bit. All right, it is known that the limit as x approaches infinity of k is -infinity. Evaluate this limit. This is actually going to be a clever L'Hopital's rule problem. So the limit as x approaches, let's look at the numerator first. What's the limit as x approaches infinity of k of x? So, well, they just told me here that that's going to be -infinity. Now, what is the limit as x approaches infinity of h of x? So if I check out function h, here's function h. It looks like that function is approaching as x is greater than 4. It's forever decreasing, so I have -infinity as well. Now be very careful that we don't say -infinity divided by -infinity equals 1 and come to the conclusion that this limit overall is going to be 1. Let's use L'Hopital's rule, because -infinity divided by -infinity is really an indeterminate form. Okay, so I don't know what that limit is. So how about this? By L'Hopital's rule, I can make the claim that the limit as x approaches infinity of the original problem is k divided by h can be equal to the limit as x approaches infinity of k prime divided by h prime. But we established earlier here that if k is an antiderivative of f, then k prime is equal to regular f. So substitution, regular f divided by h prime. Now what does that equal? So the limit as x approaches infinity of the derivative of h, that's going to be -8. And now how about the numerator? What is the limit as x approaches infinity of f? Well, remember, there's one key detail up here at the very beginning, and if you miss it, it might make this problem really hard, because we need this to understand what's going on here. It is known that f is decreasing on the entire domain, and f actually has a horizontal asymptote right here at y equals -3. Remember that horizontal asymptotes of a function are the same thing as that function's limit as x approaches infinity. They're the same. So if I know that there's an HA, horizontal asymptote, at -3, y equals -3, then the limit as x approaches infinity is going to be -3. So my limit by L'Hopital's rule is +3/8. All right, well, that'll be about a 25-minute FRQ if all 6 parts are tackled. So again, a really great question, outstanding question with a lot of different calculus concepts featured in it. I hope that walkthrough was helpful to you as you prepare for your 2020 exam.